So today we're going to start with a few questions. So this question is regarding the bias of the gyroscope. So what you see from the algorithm of the extended Kalman filter is that we are able to determine a correction in the quaternion and also a correction in the bias of the gyroscopes. So we are able to have an instantaneous correction of the bias of the gyroscope. So this means that if you look at this schematic view of the filter at the time T1, T2, you are able to have a correction of the bias, delta B, delta B1, delta B2. But computing this correction every single instant when you have a new observation from the star tracker give you a correction to the bias at that specific time. So the correction of course will vary over time. So you're measuring a bias at that time, but you will have a time variation of that bias that also give information on the drift. So this implementation of the algorithm enables also to track the random walk of the gyroscope, because you are correcting the bias of the gyroscope every single instant when you have observation. For example, yesterday we have seen that if you have measurement frequency rate at 10 Hertz, so you have 10 observations per second, you're able to have 10 correction of the bias every second. So you're able to detect the time variation of the bias and so the drift. So the other question was regarding the assumption that we have made to implement the Kalman filter in this way. So the main assumption is indeed by using the Farrenkopf model of the gyroscope. So we have that delta, so the bias itself varies over time with the Gaussian noise, eta 2. And also we have a direct Gaussian noise in the readout of the gyroscope. So when we want to determine directly omega of the gyroscope. This assumption is approximately consistent, and for example, one of the observations from the person who asked the question was if that assumption depends on the time integration of your observation. So, for example, looking at the plot of this solution, you can see that you have a fair amount of observation every second. If you have one observation every, for example, 10, 100 seconds, what happens here is that you are not able to track the variation of the bias of the gyroscope with a refined time step. So you're going to lose the information of the time variation of the drift. So in that case, that formulation probably is not fully adequate. So, but the problem here is that you're not able to provide a much more complicated formulation of the error of the gyroscope. There are possible formulations, but in principle, what it is suggested is to have a short time integration step for your observation, so frequent observation from the star tracker in order to track the gyroscope. And the combination of the gyroscope and star tracker measurements enables these the solution that you have seen yesterday, something that indeed tends to have an error very close to zero within the sigma. What you can see, for example, from this plot is that at a certain time, the errors tend to be outside the sigma. And that means that you have to reinitialize your Kalman filter. So Kalman filter has a stable behavior for a certain time step. But after a few time, you have to reinitialize in order to prevent possible divergence from your errors. And this is related to your matrix Q and R. So the problem here is that the process noise that we have introduced varies over time, and it is possible that propagating the error due to the gyroscope is not really close to what is happening in reality. So usually by reinitializing the software or the Kalman filter at a certain time enables to have a much more stable solution. But I mean, this is something that you can fully understand by running realistic case. Of course, if we're going to see that only from a theoretical point of view, you can face indeed some difficulties in order to understand fully what we mean here. But this is a general problem that you have always with the Kalman filter, because since the Kalman filter not only include the observation that you have at that specific instant, but is propagating the information that you got previously, it is always affected by the fact that the stability of the method is going to get worse at a certain time. So for example, after 1 hour, probably a reinitialization of the filter could be indeed useful. The other question was regarding the process noise and the measurement error covariance. As I said, these two metrics are related to the error measurement of the star trackers or the other sensors like Earth sensors or sun sensors. And the Q is related to the errors of the quaternions. So if you want to see as in a similar way to, to the orbit termination problem, yes, the inverse of that sigma squared could be seen as the weight of your observation. So that was the question. So yes, in principle, you can do that. But in principle, you can set your Kalman filter in a way that would provide exactly the same results of a batch filter. The only difference is that the extended Kalman filter processes one observation on one batch of observation at the same time every single step. The final question was regarding the matrix K, that, as I said, it is a combination of the covariance matrix and the mapping matrix, or the sensitivity matrix. So K is also called in literature gain of the Kalman filter, the Kalman gain matrix. So this was the other question. So concluding that, if you have other questions regarding the Kalman filter, I will be able to address that. So there is, let's see. Okay. So the...
Scusi professore.
Yes.
Una domanda sempre sul filtro. Ma
sì.
Il fatto di riottenere una stima del bias dei giroscopi ci consente di riaggiornare Q ogni tempo o lo riaggiorniamo dopo un tot?
So the question is, since we are able to update the bias of the gyroscope every single time, we are able to update the Qs of the quaternion. So the correction of the quaternion.
No, intendo la matrice Q dell'errore.
Okay. So so we are able to update the Q matrix of the quaternion of the gyroscope error. Yes. So this is actually related more to the process noise that also takes into account eta1. So delta B provides not really an information to the process noise, because basically what we are doing here is that, so in principle, that's a good question, since we are updating the information from the of the gyroscope. So in principle, what is done here is that you account for an error that is given by the gyroscope. And the error is not only given by the instantaneous bias at that specific time, but is also given by random noise eta1 and eta2 on its derivative over time. So the problem is that, so your question, it is indeed correct, because if you are able to track the bias for a certain amount of time, as you said, so for example, let's say that for 1 hour you have the tracking of the bias, and so you can have an idea on how the bias varied over time. In principle, you can think that you have some information regarding Q. The problem here is that what happens previously, if it's not really giving you, I mean, since the eta2 is also called the random walk, what happens here, what happens in this equation is that the time variation of the bias is difficult to be predicted. So you're not really able to use the information that you collected previously to update that. So you can try, but it is possible that you will be too confident to what you have estimated in the previous time, because the behavior that you have in the second hour probably will not follow the same path that you had before. That's the reason why it's called a random walk. So it is difficult to be predicted. So the best way to take into account the error is indeed that you have an initial estimate of your error given by the quaternion, and you only propagate that information. So you are basically increasing, inflating over time your confidence to the gyroscope. So what you can do indeed is it can be done that after a certain time, what you can do, you can reinitialize the Kalman filter. So what I was saying before indeed means that at a certain time, you restart from a different Q at time 0, and a different, so R will be the same because the sensors are the same. So you can indeed update your Q because you collected data in the previous hour that give you information on the behavior of the gyroscope. So basically, you don't update the Q during a certain, so when the Kalman filter is running, but usually what is done, it is reinitialized. So you restart from a certain epoch at which you re-update Q, and so over time Q will vary with the propagation matrix gamma that we have seen yesterday. So your point is correct. So in principle, you can use your observation to have an update modeling or an update theoretical, a statistical model of the error given by the gyroscopes. So basically, you reinitialize the filter in order to have a sort of retuning of the filter. Because those information indeed are useful to know how the gyroscope is behaving in that period of time. But you have to be careful because, of course, as I said, since it is a random walk, you don't have any guarantees that the next period the gyroscope will behave at the same. So usually you use, for example, scale factors in order to inflate Q, in order to be sure that you are not overweighting your gyroscope's measurements. Okay, so I hope that answers your questions. And...
Sì, grazie mille. Un'ultima cosa, quindi B diciamo ha l'uso principale di permetterci di stimare meglio omega dei giroscopi più che riaggiornare Q.
Esatto, yes. So B, the bias itself is not really related to the update of Q. So the process noise here. This is indeed so Q. You have to consider Q as a matrix that has to be taken into account in order to not underestimate the covariance matrix of the quaternion. So B indeed, so the correction of the bias is very important when you want to use the gyroscope measurements, because if you have an updated measurement of your bias, you are able to propagate from this epoch to this one with much more confidence, because this omega here will be closer to the real one, because the bias indeed is corrected. And that's the reason why you're able to increase your resolution of the measurements. But as I said, I mean, we are going really in-depth detail that will not be part of the exam or the homework. But for your future work, if you're going to deal with attitude, that will be really useful. So that's the reason why I prefer to include that part. But as I said, you don't need to know all the formulas that we have seen so far for the extended Kalman filter. You have to know especially the concept that is behind the Kalman filter. And this is very similar to what you have seen for our determination. The only difference is that quaternion enables the correction, so the error expressed as multiplication instead of a difference. That is the main difference between the classical extended Kalman filter and the multiplicative extended Kalman filter for attitude determination. Okay, so let's conclude, if there are no other questions, the Earth horizon sensors and also the sun sensors. The reason why we don't need to spend too much time on these sensors is because, okay, so actually the Earth sensors were already described last Wednesday, especially the how those sensors work. And we also have seen that in principle, the attitude determination that we have seen so far are very useful for star trackers if you use Quest algorithm, and also gyroscope if you use the standard Kalman filter. Here, what I'm going to show you is an additional method that is well suited only for Earth sensors. Because the main difference from the sensors that we have seen so far and the Earth horizon sensors is indeed that you are not able, so especially for the star trackers, so we are not going to see an object that could be approximated to a point or to a very small dot. Since we are close to the Earth, because Earth, orbiting the Earth is the only place where we can use Earth horizon sensors, we have a disk that occupies in general 45% of the field of view that a spacecraft has as when it is orbiting the Earth. So you have this large disk and you are not able to fix one point of the Earth. What you can do, indeed, you can scan the field of view and see at least 2 points. So the first point when the sensors is going to intersect the disk of the Earth, that as we have seen, it is in the infrared, the thermal infrared frequency domain. So the radiation that is emitted by the surface of the Earth and partially attenuated by CO2, because as we said, we use this specific wavelength because represent indeed a flat, provide a flat behavior, and so we are able to see the disk of the Earth underneath the spacecraft very uniformly. So what we can see here is that what we need to do is to provide a very accurate determination of the horizon. So the limb of this disk. So we need to provide very accurate determination of the point 1 and 2. This sensor works by receiving the irradiance from this frequency domain that is filtered out by a filter that is in front of the Earth sensor through a detector, and basically the detector is going to measure two phases, delta 2 and delta 1. Delta 2 corresponds to the signal that you have when the scanner is actually, so the scan path is exiting the Earth disk. The first point is delta 1. So delta 1 is when the scan is indeed collecting the first measurement of the Earth disk. So this region, so that you are looking of the Earth disk, translate in this signal that you have in your detector. So the differences, so this entire signal that you get is directly proportional to the roll axis variation. Why it is like that? Because we are assuming that our sensors is point towards the pitch angle, that basically it is assumed to be very close to the y-axis of the body reference frame. So if you have a rotation in this direction, what would happen here is that your scanner is going to intersect another region. And so you would have basically here a larger signal. So you can see that delta 2 and delta 1 give you this region. The reason why you see delta 2 minus delta 1, it is because usually it is also included a vertical reference frame. So delta 1 is positive and delta 2 is negative, is positive and delta 1 is negative. The reason why it is introduced also vertical reference frame is in order to have information of the pitch axis, because as you can see here, the entire signal received is indeed related to the roll axis. But if you want to have information of the pitch axis, so basically rotation along this axis, you need to locate a vertical axis in the sensor. So what it means, let's see if I have another figure here. So let me try to erase this one. Prego, prego.
Potrebbe disegnare quali sono gli angoli delta 1 e delta 2 se si vedono in queste figure?
Okay, so the question is, so delta 2 and delta 1 are not angles. So there is not the captioning of this figure. So this is the signal received by the detector. So it means that the scan of the sensor, so basically you are receiving a signal from the Earth disk that is received by the bolometer. So basically the bolometer will receive an irradiance here that is given by, so it's a delta phase of the signal. So you will have a signal at phase delta 2 and a signal at phase delta 1. So basically, it is the signal received by the disk itself. So it's not related to physical angles.
Ok, grazie.
Prego. So E to E is indeed the irradiance computed, so it is indeed irradiance measured by the detector. As I said, larger is the roll angle, larger will be the signal, because you can see that you're going to intersect the larger region of the disk. or lower is the angle, basically you're exiting the disk and you're going to have no signal at the bolometer. So that's the reason why you can see that the roll here is directly proportional. So the roll angle phi here is equal to E minus E0. So there is a reference E0 that is related to the altitude of the spacecraft. As I said, this signal depends on the altitude for two reasons. First of all, because if you are at different altitude, also the disk will have a different shape. So you will receive different pattern 1 and 2. So the disk will be, for example, slightly larger if you are closer to the Earth, or smaller if you are. But the main problem here is the irradiance that the detector is obtaining. So the measurement of E0 is also dependent on the distance from the Earth. Closer you are, larger will be E0. If you are at a higher altitude, the E0 will be lower. So this E0 depends on the altitude of the spacecraft. Okay, so that means that when you measure the E from the detector, that, as I said, is a function of delta 2 and delta 1, so the phase difference of the signal received by the detector, you are going to have an unknown parameter that is basically complicating your problem. So you're not able to directly determine phi because you have an additional parameter related to the altitude. So in order to solve this problem, you have to assume that you know exactly where the spacecraft is with respect to the surface of the Earth. So you should know the altitude of the spacecraft to determine the roll axis without any ambiguity. The other ambiguity is given by the fact that if you have a rotation along the roll axis by pi, you can have exactly the same pattern here. That's the reason why, that's another reason why we are going to see that we need at least 2 Earth sensors in order to determine the roll and pitch axis correctly. But before going to that detail, what we have to see here that we also want to determine the pitch axis. So if you don't have any information, additional information from this signal received by the bolometer, you're only able to provide information on the roll axis if you know the altitude of the spacecraft. But if you include a vertical reference, I will try to draw it here. So it means that this is the cone of your instrument. So now the instrument is fixed with respect to the y-axis of the orbital reference frame. So it is fixed with respect to the to the pitch angle, to the pitch axis of the orbital reference frame. So basically I took this figure and translated here. And if you have a vertical reference that is in your internally in your sensors, so you have to imagine that in the bolometer there is a sort of vertical reference. So basically you have this vertical reference. They give you a sort of symmetry by the signal that you have received from the Earth. So for example, if you have that theta is equal to 0, this vertical reference will be exactly in the middle to this received signal here. So as you can see here, we have a different angle, and that will give you 2 different receiving irradiance with respect to the vertical reference, H2 and H1. So are basically the portion of E that are on the right side of the vertical reference on the left side. It means that if you have a rotation of the spacecraft in these axes, with respect to these axes, this vertical reference is going to rotate. And basically these 2 points of intersection with respect to the disk will not be symmetric with a vertical reference, but you're going to measure H2 that is smaller to H1 or the opposite. That will depend on the sign of the pitch angle. As I said, here you have to take into account that delta 2 and delta 1 are measured with respect to the vertical reference frame. So you have always to consider delta 2 is positive and delta 1 is negative. C1, C2, and C3 are parameters related to the bolometer, so to the optics of the sensors. So you don't need to take into account those parameters. So you have to know that those parameters are directly related to the properties of the sensor itself. So those parameters, C2, C3, and C1, are perfectly known by the design of the instrument. Here you can find indeed a brief explanation of what I have said so far. So delta 1 and delta 2 correspond to a phase angle difference. So it is indeed the phase difference in the signal received by the detector. This is proportional to the rho axis, but you have to know the altitude. Otherwise, now we are going to solve this problem. So we have to assume, actually our goal is to determine the attitude of the roll and pitch axis with Earth sensors by using only an Earth sensor. So without the assumption that we know exactly where the spacecraft is in altitude. The other formula is the pitch angle that is given by this one, and as I said, those parameters are the Earth sensor constants. The other thing that you have to take into account, as I said, that you have also an ambiguity from the point 1, 2, and 1 prime, 2 prime on the left globe, as I said. So that's the reason why now we have to face the problem that one Earth sensor, one Earth horizon sensor, is not sufficient to determine the roll and pitch angles of a spacecraft altitude. So, as was suggested by one of you last week, one possibility is to add an additional Earth sensor. So, for example, assuming that you have 2 sensors in the X, B, Y, B, so in the body frame XY plane, in 2 opposite directions. So, one sensor will look at one portion of the horizon of the Earth, and the other sensor is going to look at the opposite side of that disk. You can see, for example, here that is much clearer the sub-satellite path. So you can see here that you have the ground track of the spacecraft, and also you're able to have a better explanation on what the scan path of the sensor means in terms of the 3D space. So this is the path in which you don't collect any signal from the Earth disk, and these gray pattern here is indeed the irradiance collected by the sensor when indeed the sensor is intersecting the Earth horizon disk. So this shaded area that you have here, this gray shaded area, is indeed the signal that you have to measure. By including an additional sensor, we are including 2 additional measurements. because we have 1 and 2. So the first detector will detect indeed delta 1 and delta 2. The second detector will determine delta 3 and delta 4. So we're going to detect exactly 4 measurements to determine 3 parameters. Why are 3 parameters? Because as I said, the parameters that we have to solve in this case are the phi angle, the altitude of the spacecraft, that is, they give you these constant, these scale factor E0, and also theta. So we need to solve for 3 parameters, and before we had only 2 measurements, delta 1 and delta 2. Now we have 4. So we have indeed much more measurements. So we have 1 more measurements compared to the unknown. And as you can see here, by using exactly the same formulation that we've seen so far, the roll axis, the roll angle is directly related to the phases delta 2, delta 1, delta 4, and delta 3. So we basically removed the dependency from A0H. We were able to determine this parameter by combining the phi angle that was determined by the same formulation by using delta 2 and delta 1, and on the other side, delta 3 and delta 4. Since E0 is the same, because the spacecraft altitude is the same for both sensors, we are able to cancel out this dependency. On the other hand, we are also able to determine the pitch axis. So the pitch axis is also determined by these 4 variables and has a similar expression of what we have seen before. One of the main advantages of this configuration is indeed that we have 1 more observation compared to what it is required. One of the advantages of this configuration is indeed that since you have that the spacecraft is moving along its orbit, the Earth, so for example, here yesterday I tried to explain that if you have the sun here, the detection of these 4, so the frequency delta 4 could be very could be indeed a problem, because you have also thermal emission from the sun, and so when you want to determine these the end of these so to detect the horizon limb at this point here, let's say that this is 4, of course you're not able to determine that with a very accurate precision. So, for example, this point will not be useful. But if you have 2 sensors, you have at least 3 measurements that are enough to determine the roll and pitch axis angles of the spacecraft. So this additional term represents a good redundancy to enable determination of the roll pitch axis with Earth horizon sensors, so 2 axes, 2 Earth horizon sensors. In the next hour, we will start by seeing that, of course, your goal is always to minimize the number of sensors, and so mass and power budget for every single instrumentation. So one possible solution to have the same advantage of a dual Earth horizon sensors is combining these advantages in one design. So by having a dual scan Earth horizon sensors. Dual scan means that compared to the previous design that we have seen so far, the mirror, there is a rotating mirror that enables the scanning of two different field of view. The main problem with this instrumentation compared to the previous two Earth sensors is that you're not going to look at two different portions of the limb of the Earth horizon, but you're going to see basically similar portion with two different field of view. So the main problems that you have to deal with these parameters, with these sensors, is indeed that some of the so one of the two measurements can so one of the 2 points of the 4 Earth horizon limb intersection could be indeed be actually perturbed by the light, so light interference coming from the sun or the moon, for example. So this dual scan configuration enables to have at least 4 measurements. So if you have that one, it is indeed interfered by the Earth, the sun or moonlight, you are able to have anyway enough measurements to determine the measurements of the roll and pitch axis. So in the next hour, we're going to see a method that you can use for these Earth sensors to determine the roll and pitch angles by using those sensors. So in principle, what you can do is that if you get the angles, so you get indeed the vectors of the intersection of your Earth sensor scan with the disk of the Earth, you can use this vector in a triad algorithm, or in a quest algorithm, or also in the extended Kalman filter. But you can see here that we can find a simpler approach in which you directly use these 2 vectors to determine the roll and pitch axis only. So it will not be a 3D determination of the attitude of the spacecraft, but will be only the roll and pitch axis. So let's have a break here. Okay, so the question, so I got 2 questions so for during the break. So the first question was regarding E0 for the Earth horizon sensors. So the question was that if E0 is decreasing or increasing with the altitude. It is decreasing with altitude because it is directly related to the irradiance of the thermal emission of the Earth. So if you are higher, you're receiving less irradiance. And so that's the reason why you need to know precisely where you are, because that will give you information on that, on the signal that you are receiving from the Earth. The other questions is regarding the physical meaning of the gyroscope models. So it is clear, for example, from the Farrenkopf model that the K is coming from the electronics. The reason why we didn't give a comprehensive explanation of the physical meaning of the different terms is because the eta1 and eta2, so the angular random walk and the rate random walk, depends on the instrument and the instrument technology. If you want to have an idea, we have reported, for example, the values for the angle random walk of the resonating gyroscope. So the resonating gyroscope is indeed very, as I said when we described the resonating gyroscope, is very stable over time because of for example, the fact that these, so the variation of the spin rate of the spacecraft is measured by using the effect of resonancy that you have for a shell that is vibrating with specific patterns. So that mechanism enables lower random walk. If you want to have a comparison with another instrument, that could be useful to compare with the fiber optic gyroscope. As I said, in space, you have a very different thermal environment, especially if you go from cruise to a planet like Venus, Mercury, or others, that you have a larger thermal gradients. That leads to variation of the length of or basically, yes, the physical length of the fiber optic coils. And this variation over time is indeed responsible for the both angle and rate random walk. So the values, so if you want to have a physical meaning of these two parameters, you have to put in the context of the sensor itself.
Ok, grazie.
Prego. Okay, if there are no other questions, we can. Okay, let me. Okay, so the main goal of the last part of the Earth Horizon sensors is to provide an additional explanation on, or an additional method to use the Earth Horizon sensor to determine the roll and pitch axis. I know that this figure may be too complicated, but so let's recap what we have seen so far. So the YS correspond to so we now introduce the sensor reference frame. As we have seen so far, we have seen that the Earth sensor is placed to the axis of the body frame, so Y, so YB. The YS that you see here is not exactly that, but here the YS corresponds to the reference frame of the sensor. So the sensor itself has a conical path that we have seen so far with a vertical reference frame. So this dashed line that you have here. So if you want to have a physical explanation of delta 1, you can indeed convert to basically the delta, the phase signal, the difference that you see in your detector as this angle delta. So delta 1 and delta 2. The axis of the sensors, you use, for example, that YS is parallel to the bore side of the sensor head. So it is basically in the middle of the conical path. And the conical path has an angle that is called eta. The XS and the zeta S are selected to form basically an orthonormal triad that give you, for example, the plane in which you will collect your measurements. This instrument, after that, is placed in the reference frame of the spacecraft. So now this reference frame here is placed in the middle, in the center of the spacecraft. And we need, as we've done for previous problem, to determine the we need to determine the attitude of the spacecraft with the specific reference frame. What we've done for star sensors and in general by using the triad and BABA problem or the extended Kalman filter, we assume that the reference frame that we want to use was indeed the inertial reference frame. So in previous problem, we have determined the rotation matrix from the ICRF to the body frame or the OBF. So for example, this is for star trackers and so star trackers and other sensors. Here, the reference frame that we want to use as our reference is not the inertial reference frame. Since the goal for this procedure that we're going to show is to determine the rotation matrix from the reference frame that we can call Earth reference frame, the Earth frame, to the sensor, so SCF frame. So basically, what we want to do here is to determine the altitude of the spacecraft with respect to that reference frame. This Earth reference frame is not fixed fixed to the Earth, but basically what we need to consider is it could be indeed the reference frame of the for example, the orbital reference frame of the spacecraft. So what we are going to do here is that this is the spacecraft. We'll have a certain distance from the center of the Earth. It is that will be the radius of the Earth plus h. Okay, so the spacecraft is here, and the reference frame, the zeta axis of this reference frame will be indeed in this radial distance of the spacecraft from the center of the Earth, and so will be called minus zeta r. So it will be closer to the y-axis for the orbital reference frame. And we're going to use, we are going to place the sensor reference frame minus zeta s parallel to this axis. The axis ys, so the both side axis of the Earth sensor, is indeed orthogonal to that, and usually it is assumed to be very close to the y-axis of the body. And so since the body usually wants that the y-axis of the body frame is close to the y-axis of the orbital reference frame, so for example, or actually the pitch axis, you can assume that this ys is very close to your yb that we've seen so far, and so also the pitch axis of the orbital reference frame. The other two axes of our reference frame indeed are assumed to be xr and yr. So as I said, you can use yr very close to your pitch axis, and xr will form the orthonormal, so the third axis of the orthonormal triad xr, yr, and zr. So the two axes that you are defining are zeta r, basically along the radial distance of the spacecraft, but is a minus here, so it is minus zeta r. This is a yr that is can be considered as the axis, the pitch axis of the orbital reference frame. And now the problem that we want to solve here is to determine the crossing points of our scan, that basically is defined by this ring here, to the Earth disk. So this is the projection of the Earth disk as seen by the spacecraft. So what you do here is to define vectors, or indeed unit vectors, that basically connect the center of the sensor to the intersection point on the Earth horizon for in the reference frame xr, yr, and zeta r, and also in the sensor reference frame. If you define these two unit vectors as S, so S1 and S2, those two sensors, those two unit vector will be indeed the vector, the unit vector from the center of the sensors to the intersection of the cone, the scanning cone, to the Earth disk. So the Earth disk, in order to determine indeed that will represent your measurement. So what the sensor is measuring at that specific moment. But you also need to know the unit vector of this intersection point in the reference frame xr, yr, and zeta r. that, as I said, could be close to the reference frame of your orbit, but is that basically that will enables a comparison between the vector expressed in this reference frame and the one that you are measuring from your sensors. So let's write down these vectors. So from one side you have that the v that always express the unit vector in the known reference frame. In this case, will not be the ICRF, but it will be, for example, as I called here, this EF, Earth reference frame, that was defined as I said before. You can see that this unit vector could be easily defined by using two angles. The first angle is rho. Rho indeed is the angle that is between the minus zeta r and the unit vector v1. So it is this vector here. So it's basically a sort of, it's the opposite of the elevation of a vector, basically, because it is, actually could be seen as the elevation vector between this axis and v1. You're also able to measure beta. Beta here is indeed the angle between the YR axis and your vector. So this vector here could be seen as an azimuthal angle in the horizon plane. That's the reason why this reference frame is centered to the horizon of the Earth. But for now, both beta and rho are not well known, of course. Oh, actually, you know, you have to find a way to indeed determine these parameters, rho and beta. What you get from your sensor, you are going to get directly your angles delta 1 and delta 2. Those angles are directly related to the unit vector measured in the sensor reference frame. So if you write so basically represent your W in your triad problem, but it's called the sensor because, as we said, there is an additional rotation from the sensor reference frame to the optical bench frame. So if you want to have a W, you have to multiply S by this additional rotation matrix that is known because the reference frame of the sensor is known. The other angle is eta. Eta is known because it's the cone, cone angle that is the design that is given by the design of the sensor itself. So eta is known, delta is measured by the sensor. You are able to determine the unit vector of the crossing point with respect to the sensor reference frame. So we have indeed to determine these. We have now two unknowns. The first unknown is rho. The second unknown is beta. We can easily demonstrate that rho is only given by the altitude of the spacecraft. Indeed, if you consider this triangle here, you can see that if you do oh, actually, sorry, it's not the triangle because you need, so let me cancel out. So what you want to do indeed is that you know that this distance is RE. So the distance from the center of the Earth to VI is known, that is the radius of the Earth. So you have this triangle. And you have also the that actually you can directly determine by using, so basically this is the you consider that these triangles indeed given by also the altitude of the spacecraft, so this one, you are able to relate this angle rho to the known radius of the Earth, but the unknown altitude of the spacecraft. So basically, you know that rho, so this is the altitude equipotential of that specific point. So you are able to determine indeed that the sign, that this distance times the sine of rho is equal indeed to RE plus the equipotential altitude. So basically you have that this rho is only given by the altitude of the spacecraft. So the spacecraft altitude is the only unknown. And if you know the altitude, you're able to fully determine this parameter rho. So the only unknown in this versor, in this unit vector expression, remains beta. Okay, so here is expressed even further what we need to do, and you can find indeed that we need to determine the transformation from one expression to the other one to determine the unknown parameters. So to determine S from the vector V1, you need to transform, you need to rotate this vector, that is your S, so your measured S, that is known because this is measured by the detector and this is given by the design of the instrument. And those are the pitch and roll angles. You can write that this expression here is equal to V1. So basically by using two additional, so basically by doing two rotations along the x-axis and the y-axis, so we are assuming that basically you are going to rotate this vector by the roll and pitch axis, you're able to determine the unit vector S in terms of the reference frame XR, YR, and zeta R. So what you can see here is that this relationship only depends on theta and phi that are indeed our unknown. Okay. So what we need to do here is that you can easily find out that in order to determine the basically the vector of the unit vector, so basically the attitude of the spacecraft, so the angle theta and the angle phi, you have not only two unknowns, but you will have indeed three unknowns. So theta, phi, and rho. Because as I said before, rho depends on the altitude of the spacecraft. So it's basically the same problem that we have seen before, but the only difference that now we can directly compare the vector that is seen by the sensor frame and the vector that is seen by the Earth reference frame. So what you can easily see here is indeed that the third component, for example, this vector. So if you multiply these two matrices to this vector, you have this expression here that will be equal to the third element of the vector expressed in the XR, YR, and the ZR reference frame. So you can see that you have indeed three unknown, two unknown that are phi and theta, and an additional unknown that is given by rho. So the main goal here is to show that not only in order to determine the attitude of the roll and pitch axis, you need to have at least three vectors, because of course, if you want to determine also the roll axis, you need to have an additional term that will not be only S1 and S2, but you need at least another S3 in order to fully determine the attitude by using this very rough attitude determination method. So this only demonstrates that, in principle, the Earth horizon sensors is able to give you the attitude of the spacecraft by using, for example, three crossing points of the Earth horizon. So if you have these three crossing points, you will have enough equations in order to determine the roll axis angle, theta, the pitch axis angle, and rho. If you know rho, that will become indeed a known parameter, and so you have enough equation to determine the theta and phi axis, phi angle axis. So this is only a very quick demonstration. If you want to use Earth...
Scusi, professore.
Prego, prego.
Ma se noi abbiamo tre equazioni perché abbiamo vettori tridimensionali, perché non basta uguagliare elemento per elemento per ottenere le tre equazioni in tre incognite?
So the question is, so if we have three vectors and we have, so basically if you, three vectors, what do you mean? Quali tre vettori?
No, non tre vettori, noi abbiamo posto l'uguaglianza V1 uguale
le
a...
tre componenti, giusto?
Esatto.
Okay, so the question is, if we have already three components to determine the basically to determine the attitude of the space of these bursts, or here V1, those would not be sufficient to determine all those parameters. Well, the answer is not, because basically, first of all, these vectors, in order to be, well known, should be unit vector. So you know that one of the you have a degeneracy because basically one of the two components basically is fixed, because you are assuming that you are using unit vector. And first of all, and furthermore, is that, that would be a good exercise, for example, for you to so here we don't report exactly or all the expression, but you can indeed do as an exercise to find out that when you use the, for example, only two elements, so only two vectors, in that case you will have four equations, because in that case you have indeed you have four equations, and basically because you have that two unit vectors are equal to 1, but as we have seen before, there will be not enough. You can already see with this example here. So basically that approach only tends to explain what we have seen so far in the previous modeling. So you will have exactly the same problem, that your rho will not be fully determined if you have only the crossing point 1 and 2. So you have to include an additional point, because basically that equation will still be an unknown parameter, and in your final goal basically is to use an additional vector, so let's call it S3, to include an additional equation that indeed is important to determine this raw parameter here. Probably there will be, we can also have a separate short discussion after, I mean, to have a discussion afterwards, but in principle, I think that the main point here is indeed to show you that the same approach that we have seen, so the same conclusion that we have seen with the previous approach is also, can also be demonstrated with the expression of the vectors in this reference frame. So basically the problem is that the problem that you have always is the same problem with the triad algorithm. So you need at least 2 observations to determine the 3D determination. Here you need more than that, because your unit vector S do not provide the uncorrelated position of a point, but basically a point S1 or V1 and V2 are correlated because are both on the same horizon plane. So those, as I said, if you explicit basically these product of matrix with this vector to the vector V1, you can see that not all the equation will give you unique information, but you will have a sort of degeneracy that will require an additional measurement, for example, as I said, S3, in order to have 3 equations for 3 unknowns, so that there are phi, theta, and rho. So if you have only S1 and S2, you can fully determine theta and phi, but you have to assume that you know where the spacecraft is, because you have to know how much is rho. So we are not able to provide all the equations, but this is another approach to basically have clear what we have said before. So basically that this configuration is fundamental to have an accurate determination of the roll and pitch axis. We can have a further discussion afterwards or early tomorrow about that. But let's go to the next sensor, because we need to conclude this part today. But if you have any questions, additional questions, we can continue to discuss about that. I mean, I understand that it is really important for a comprehensive understanding. So the main point here is indeed that the Earth sensors give you the possibility to determine uniquely the roll and pitch axis of the spacecraft. And the accuracy they usually get are a portion of a degree, for example, 0.015 degrees. And the main error sources that are given by the Earth sensors is given, for example, by this parameter H equipotential, because basically the distance of the equipotential, so the equipotential distance of, so basically H EQ represents the, it's not really the, it's not for equipotential, but basically is the altitude at which it is assumed that you have your infrared emission of your infrared emission. So basically represents an equivalent altitude at which you think that your infrared thermal emission is coming from. So, for example, as I said, an error in the in this region here. So if you have that your horizon limb is responding differently from region to region, that can indeed lead to higher errors. For example, to 0.02 degrees or up to 0.5. So the indetermination of the horizon limb indeed represents one of the main error problems, error factors. And that represents indeed one of the main problems for these sensors. Anyway, that's the main problem, because basically you have to deal with a disk and not with a reference object. And so you have the advantage to have something with a larger signal, that is the Earth disk, but with very high noise, given by the fact that the determination of the limb is indeed very noisy. These are here, for example, one of the configuration of the Earth sensor that show you the stability in temperature and also the power consumption and power supply. As also interesting is the mass. So you have to consider that usually these sensors has a very compact design. So to conclude the part on the altitude determination, we have to discuss briefly about the sun sensors. Briefly, because the concept that is behind the sun sensors is really simple compared to other sensors. So the main concept that is behind the sun sensors is that we are going to look at the sun and use its known position knowledge in order to determine basically the vector W from the sensor and compare with our a priori knowledge V. So that configuration, the configuration of the sun sensors is indeed very well suited for the triad algorithm or the quest algorithm. The main problem here compared to the stars is that we don't have a small so a very small shape of the body, but we have that the body itself has a specific, basically a specific disc shape that represent an advantage if you want to have a simple instrument. For example, if you want to have only a sun detector, so basically detect if your sun is in your field of view, that represents an advantage because you can see if the sun is moving along this sensor, and you're able to have a rough estimate of your altitude. For example, that was very useful for Earth satellites that have, for example, non-demanding altitude determination requirements. But if you want to have something more precise, usually you want to determine indeed the vector W, so the relative orientation of the sun with respect to the optical bench frame. The sensor itself consists of a photocell that basically a photocell that consists of that enables to track the position of the sun with respect to a vertical axis. So a very simple concept of the sun sensors consists indeed with a photocell that is able to detect the irradiance of the sun. And so you can measure that with the photocell, and you can see that the expression of this pattern is related to the incident angle of the sun ray with respect to the vertical reference frame. So if alpha is equal to 0, you have vertical intersection of the sun to the photocell, and you have the maximum intensity that you're able to measure I0. This larger is alpha and lower is the signal that you are receiving. And so usually this kind of signal has a trend equal to the cosine. So if you do I0 cosine alpha, you're able to determine this solid line that represents actually a theoretical model of the photocell response. In reality, when you have a larger alpha, you have a different response. So that is very close to this dashed line. The different response coming from the fact that indeed you are not able to have exactly a cosine trend, but you have something a little bit different given by the imperfection of the photocell. But the main problem of this configuration is that a single photocell gives you a strong ambiguity of where the sun is, because you have the same signal if you have plus alpha or minus alpha. If you have minus alpha, the signal will be exactly the same. So in order to prevent from this problem, what you need to do is to include at least 2 photocells. If you include 2 photocells by using different inclination, for example, by using this configuration that you had here, so the two, you basically consider a vertical axis of the instrument called N, and you locate the vertical axis of each solar cell on the right side with an angle plus alpha 0, and on the left side minus alpha 0. What you can see here is that when you have an intersection of the light from the sun, the response that you get, so the output current, because the output of the detector is the current that you get, as for example when you have a solar array, you can see that the final output will be a solution that will be a sum of 2 cosine terms. The first cosine term is given by, for example, this solar cell here. So we'll have these path here. The other one is having exactly the same basically is actually having exactly the same behavior with the cosine term that we have seen before. The only difference that the output current corresponds to delta I. So we are doing the difference between I2 minus I1. That's the reason why you see that in the opposite side. What you can see here is that if you do I2 minus I1, what you get is that one cell is going to see an angle that will be alpha 0 minus alpha, because basically the intensity of one sensor, as we said, so the current that one sensor generates is I0 cosine of alpha, where alpha is the angle with respect to the reference frame of the solar cell. So since here alpha probably could be misleading, is the angle, so here alpha is with respect to is with respect to n and not to the array, to the vertical axis of the single solar cell, you can see that if you do the difference in current of I2 minus I1, you get a constant K that corresponds indeed to your I0, so your maximum current that you get when the rays are exactly perpendicular to the solar cell, times cosine of alpha 0 minus alpha. You can directly compute it very easily because you know that this axis is alpha 0, so this angle here is indeed alpha 0 minus alpha. The angle that the other solar cell sees is alpha 0 plus alpha. So if you do the difference of the two current, at the end you can transform with the cosine and sine formulas to be 2K, so twice the intensity, the current that you have at maximum, times sine alpha 0 times sine alpha. So since sine alpha 0 is also a configuration given by the instrument, so is a known parameter alpha 0, you can write that K sine of alpha 0 is indeed equal to, actually 2 is equal to this constant. So you have a sinusoidal trend, but you have a sinusoidal trend only in this range of angles between minus delta alpha and delta alpha. Why you have this range of angles? Because you have to consider that the solar cells are not able to detect any signal at angles lower than gamma. So there is a threshold here, so you're not able to measure angles close to 90 degrees, but you will have a certain tolerance that is given by gamma. So you can easily compute what is indeed what is the amount of this delta alpha, because you can from this triangle here determine that this is also delta alpha. So the triangle that is given by this vector here, these sides here, will have that delta alpha plus alpha 0 plus beta, where beta is this angle, so this angle here is 90 degrees, okay? This angle here is beta, plus 90 degrees, so the sum of these angles has to be equal to minus 180 degrees. So you know that beta cannot be lower than gamma, so you know that you are not able to find any angles that are 90 degrees minus alpha 0 minus gamma. So basically here, assuming that beta is equal to gamma, you can find indeed that at angles larger than delta alpha, you are not able to distinguish between the two signals. And that's true, because if you do, for example, this one minus this one, you get indeed you get indeed an ambiguity in the signal of the sun sensor, because this one minus this one give you indeed exactly, so basically this one minus this one, since this one is 0 for this angle, give you this value. At angle larger than delta alpha on this side here, since you have to do this signal minus this signal, these two amplitudes are equal, so you are not able to disentangle the effect that are outside these two delta alpha. So basically, the only region at which you are able to use the sun sensors to get the orientation, unambiguously the orientation of the sun with respect to the sun sensor normal, is indeed this region between minus delta alpha and delta alpha, with delta alpha given by this relationship. So you have to be careful that you're able to have a linear, or I mean, it's not linear, but a very close to linear trend of these sensors in these angles. But as we are going to see tomorrow, this represents only part of the problem, because so far we have only determined the orientation of the sun with respect to one axis without ambiguity for this range of angles. But we will need to determine the orientation of the sun, so the unit vector of the sun. So we need an additional angle. So we will use, you can use two sun sensors with this configuration, or as we can see tomorrow, a different orientation, a different configuration of the sun sensors. So tomorrow we are going to conclude this part of the attitude determination, and we are going to start the attitude control that will be indeed focused on the attitude control devices and other and also a few techniques to determine the control of a spacecraft.